Hello, welcome to Einstein's Mechanics. In this episode, we are going to look at nodal analysis with voltage source. In our previous episode, we talked about nodal analysis without voltage source. In this episode, it will have a voltage source. How do we go by it? First, we know all the rules for nodal analysis. We select a reference node. We select a reference node, and we know that at the reference node the voltage will be equal to what? 0. Then we also apply our KCL to each of the non-reference node. Are you okay? The non-reference node. So we know all of this from the previous episode. Now, if we have a voltage source in the circuit, how are we going to do the analysis? Now, let's look at some rules that are going to govern analysis with voltage source. So our rule 1 is going to be, if a voltage source is connected between the reference node and a non-reference node. So for example, let's take a node, this point as a node, and this point is also a node, and there is a voltage source. Let's say a plus and a negative voltage source, and this is a 5 volt. This is non-reference node, and this is the reference node. So non-reference node, we have it this way, and this part is also the reference node. And the rule is saying if a voltage source is connected between the reference node and the non-reference node, the voltage source is simply set to the voltage at the non-reference node. It's very simple. So in nodal analysis, we know that we always select a reference node. And here, if you see any voltage source connected between the reference node, that means the node that has the 0 voltage, and any other non-reference node, the voltage source, let's say here is 5 volts. This 5 volt is going to be set to the voltage of this non-reference node. So this node is going to be 5 volts automatically. Are you okay? It's very simple. So in any circuit, let me just have a simple circuit such as this. I have my resistors, and I have a resistor, I have a voltage source, a plus and a negative, something small to explain this. So this is also a voltage source, say plus and negative, and I close my circuit in this form. Are you okay? So now when you look at this diagram, this is node 1, this is node 2, and this is node 3. Do you see that? And this is our node 4. So the rule is we are to ground or use one node as the reference node. So I'll prefer to use this node as my reference node. So I only have node 1, node 2, and node 3. And the rule for nodal analysis with voltage source is anytime a voltage source, this is a voltage source, this is a voltage source. What we are saying is anytime you see a voltage source connected between a reference node, this is a reference node, and a non-reference node, this is also a non-reference node, then the value of the voltage is set to the non-reference node. So in the analysis here, we are going to say the voltage at the node 1 is simply 5 volts because this voltage source is connected between the non-reference node and the reference node. Is that okay? So very simple. Now, that's for the first rule. What if the node or the voltage source is connected between two non-reference nodes, such as this case? This voltage source, what do we do? If the voltage is connected between two non-reference nodes, you can see that node 2 is a non-reference node, right? Node 3 is also non-reference. The only reference node is this part. So in such cases, what do we do? Here, what we are going to do is we are going to, if the voltage is between the two of the non-reference node, then these two nodes, the node 2 and node 3, they are going to form what we call a supernode. A supernode. Are you okay? So here node 2 and node 3 are forming a supernode. Why are they forming a supernode? Because we have a voltage source between the two nodes. Are you okay? A voltage source is between, this is the voltage, the two node 2 and node 3. And when we say they are forming supernode, this is what we are going to do. Anytime we are considering the supernode, we are going to assume as if they are forming a single node. So whatever current is entering into the node is going to be assumed as a single node. Do you understand? You will solve examples and you understand. So for example, if here current is coming, let me clean so that you can see the diagram. So let's look at this diagram. So let's say we have current this way, current that way, current leaving, say current moving. Can you see the current? So here the supernode is node 2 and node 3. They are forming the supernode. So during the analysis, remember we apply KCL to a nodal analysis. When we are applying the KCL to this node 2 and 3, because they are supernode, they are going to be applied at the same time. So whatever current is moving into node 2 is going to be added to whatever current is moving into node 3, and that should be equal to whatever current is leaving node 2 plus whatever current is leaving node 3. It's very simple. So we treat the nodes as one. That's what we are saying by it forms a super node when we have a voltage source between the two non-reference nodes. So all these rules are going to be applied in nodal analysis with voltage source. It's very simple. Once you get it done, you are good to go. Let's look at an example. So find the node voltages and currents in each branch. So we have our diagram over here, and we are to find the node voltages and the current in each branch. Remember, once you find the node voltages, it helps you to calculate for the current in the branches. So let's look at how best we can do this. Now I have my diagram, and I will prefer to use this diagram as my redrawn diagram. You can redraw the diagram, but I'm going to use the same diagram. So what we see is, first we have to identify the number of nodes. Here we have node 1, node 2, node 3, and node 4. Are you okay? So our first idea is to ground one of the nodes and make it the reference node. So I'll prefer to ground this part and make it the reference node. So that will be voltage here will be equal to 0. Now I have how many nodes left? I have 2 or 3 other nodes, which is I'll call voltage here as V1 at node 1, V2 at the node 2, and V3 at the node 3. You can see that there is a voltage source here, and there is also one voltage source here. Both rules are going to be applied in this example. So let's look at it. Now, we have to assign currents so that we can express or apply our KCL with the current directions. Is that true? Yes. But take into consideration, anytime you are solving the node voltages and you have a voltage source between or in any branch, don't assign current to that branch. For example, this branch already has voltage source. This branch is also having a voltage source. So in our current, as when we are assigning current, we are not going to assign current to that branch. It's simple enough because the idea of assigning current is to help us express the current in terms of voltages. But being so good, we already have the voltage in that branch. So what is the essence of assigning the current again? Do we understand? So here I'm going to assign my current, and this is what we are going to get. This voltage source is going to produce current, and this current is going to, we can see that naturally it is going to be up, but because there is a voltage source, I won't assign that current to this branch, and it will be in this form. This current will pass through this part and this part. So I will call this as my I1. We know that I1 is also going this way, and it is going to split this part and this part. But because there's a voltage source between or in this branch, I'm going to forget about the current being assigned. Are you okay? So I'm going to call this part as my I2. I2 is also going to split in this direction. I will call it I3, and I'll call this one as my I4. So this is the current. So you can see that the two branches with the voltage source, I did not assign any current because the voltage is already measured. So once we have this, then we are good to go. So rule 1, the first rule that governs the node analysis with voltage source is saying that if there is a voltage source between a non-reference node and the reference node, we set the voltage to the non-reference node. So that means that with that idea, we can simply say that V1, with that idea, we can say that V1 is equal to 10 volts because the voltage is between V1, which is a non-reference node, and the reference node. Is that true? Okay, so now we have voltage at the node 1. What about node 2? So now I won't bother with the first node again with current and any analysis because I have it. I'll come to the node 2. Now at node 2, remember between node 2 and node 3, a voltage source is there. So they are going to form a supernode. So a supernode means I'm going to consider the nodes as 1. Pay attention here because it's very confusing. Supernode is node 2 and node 3. They are forming just a single node, meaning whatever is going into node 2 is going to add to whatever is going to node 3, and whatever is leaving node 2 is going to add to whatever is leaving node 3. This is what I mean. So considering node 2, I can say I1 is entering, right? So I1. So at the supernode. So at the supernode, I can say that I1 is entering. And you can see that at the node 3, I4 is also what? Entering. So it is going to add to I4, which is entering. And that should be equal to, when you look at node 2, I2 is leaving. So this is equal to I2. And when you look at the node 3, I3 is also leaving. So going to add I3. So we are treating that node as a single node. It's clear enough. So now that we have our KCL, it is very simple for us to apply. So we are going to express the current in terms of what? Voltages. So I1. In terms of voltage, we know that I is equal to the voltage on the resistance. So I1, looking at the direction of I1 is between the voltage 1, 2 minus voltage 2, and the resistance is what? 2. Now we look at I2. So I2 is also between the V2 and the reference. So that was going to be V2 minus 0, which is also the same as V2 passing through the resistor 8. We've already talked about many of this in the previous episode. So now we can also talk about I3. And looking at I3, it is also moving from V3. So that will be minus the reference, which is 0 over 6. And I4 is going to be, I4 is moving from V1 all the way to V3. So that will be V1 minus V3, all on the resistor, which is 4. So that's simple enough. And we can now bring them back into the equation. So that is going to give us as I1, which is V1 minus V2 on 2, plus I4, which is also V1 minus V3 on 4, equal to I2. And I2 is V2 on 8 plus I3, which is V3 on 6. Now, we know that from this equation A, we know that V1 is equal to what? 10. So we can bring the value of V1 into the equation. So now that is going to give us V1, which is 10 minus V2 on 2, plus 10 minus V3 on 4. Should give us V2 on 8 plus V3 on 6. When we simplify this equation in terms of V2 and V3, we are going to get V2 minus, let's simplify it, and this equation is going to give us 3 times V2 plus 2V3 equal to 36. Let me call this equation 1. So we have V2 and V3, and we need two equations to solve for the unknowns. Now, the second equation, we are going to get it from, look at this branch. The branch which is V2 and V3. The voltage between these 2 points, these 2 nodes, is measured to be what? 5 volts. Do you see that? It is measured to be 5 volts. And when you check the sign inside the voltmeter, you can see that this part is positive, this part is what? Negative. This means that the V2 is of higher potential than the V3. So what this means is that, so we can also what this means is that the voltage measured, which is V2 minus V3, is equal to 5 volts. It is also measured. So we can get this as equation 2. So now you can see that equation 1 is in terms of voltage V2 and V3, and equation 2 is also in V2 and V3, and solving it simultaneously. So solving equation 1 and equation 2, we are going to get our V2 to be equal to 9.2 volts. The rest is mathematics, and our V3 is going to be 4.2 volts, whereas we already have V1 from the circuit as 10 volts. Do you see that? So once we have this, then we can also talk about the currents, because already the currents are expressed in terms of voltages, and now we have each of the voltage. We can put in the values, and straight away we can calculate for the value of each of the currents. So let's look at how we can get the current. We know that I1 is going to be V1, which is 10 minus V2, which is 9.2, all on 2. And that is going to give us a current of 0.4 amperes. Now, I2, which is V2 on 8, V2, which is 9.2 on 8, and that is going to give us 1.15 amperes. And I3, which is V3 on 6, and V3 is 4.2 on 6. This is giving us 0.7 amperes. Our I4, that is going to be V1, which is 10 minus V3, 4.2 on 4, and our current is 1.45 amperes. So this is the first example on nodal analysis with voltage source. Check out for the next episode. We have 2 examples solved on nodal analysis with voltage source. See you. Subscribe to the channel, like our videos, and share with your friends. Thank you for watching this episode.